Hello, everyone. My name is Oliver, and welcome to the Q&A with Redwood Research CTO, Buck Shlegeris. Buck previously worked at MIRI, studied computer science and physics at the Australian National University, and grew up in Townsville, Australia. Please join me in welcoming Buck. So as this is a Q&A, please put any and all questions in the swap card chat in the question link. And as the audience writes their questions, Buck, could you first give us a sense of how you view the problem of alignment?
Yeah. So here's my overall sketch of the beliefs I have about the AI alignment problem and what it looks like. I tried this morning to come up with a new articulation of a bunch of this. So some parts of it might be new and flawed, but I'm excited for this phrasing of everything. So to start with, I want to clarify that the thing I'm about to say is the sketch of the reason why I believe the stuff that I believe, rather than like the short version of the argument. It's like a proof sketch in the sense that the beginning of a math paper with a long and complicated proof might have a rough sense of where the argument is going to go. It's a map rather than trying to claim to be a very short proof. And so that's very much where I'm at. I'm just trying to have it so that people are going to know the way that these ideas are structured inside my own mind. If you want a better, longer version of a bunch of these arguments, I think I particularly recommend some of the stuff Holden Karnofsky has written on his Cold Takes blog in the Most Important Century series recently. Ajay Kotra from OpenPhil also has a long post on some stuff about AI alignment, which is going to come out in about a month, which also makes a bunch of the arguments that I'm going to say here in a much more detailed fashion. So overall, so I want to start out by talking about artificial intelligence and ignoring the concept of machine learning. So artificial intelligence is basically just the hope that we will, or the possibility that we will eventually find a way of automating the human actions of doing intellectual labor. So for example, doing science and technology development or making decisions based on understanding of the world derived from experience and observation. And I guess like the first claim with artificial intelligence is that people will try and then succeed at building systems which can automate this type of activity, basically because we can probably build systems that are cheaper and better at doing it. So in the same way that humans have substantially automated the process of moving heavy objects from place to place. We have trucks, we have forklifts, and so on. And this is a mixture of the fact that we can move heavier things. We can do the move heavy objects task both better and more cheaply. Similarly, I think that humans are strongly motivated to come up with ways of doing science and technology and decision making better and more cheaply. So building systems which are able to do decision making and science and technology development better than humans can probably requires, according to me, building systems that have long-term goals and consider cleverly different options of ways that they could act that are going to cause them to succeed at achieving their long-term goals. And this is a somewhat scary type of situation to be in because if we built these systems and they turned out to have goals that were not compatible with our goals, then they would be incentivized to act in ways that caused them to have control over the future instead of us. And so the situation would just be kind of like, imagine that you're some nation and there is a hostile neighboring nation and you have stuff that they want. You might end up in a war if they think that they can beat you in a war, just because you have stuff that they want. It seems to me like this is kind of the default concern with AI, that we're going to try really hard to build systems that maximize goals. And if these goals are not aligned with ours, then we find ourselves at war with a more advanced species. I think like the tagline for this perspective on the AI alignment problem is yes, like in the Terminator. I think a lot of people like have talked about AI alignment trying to distance the concept from the concern that you might build these AIs that just want to kill everyone and take their stuff. But from my perspective, that is in fact the main concern. So we're trying to build these really powerful AIs. And this is kind of like a really weird principal agent problem or like a mechanism design problem in economics. So in economics, like a principal agent problem is something like, I want to sell my house. And in order to do this, I have to hire a real estate agent because I just don't know anything about the local housing market. And I try to come up with some scheme for paying the real estate agent such that they're going to do a good job of finding like a good price for the house. But in fact, typically the deal is you just pay the real estate agent 6% of the sale price of the house or something. And so they aren't incentivized to, for example, spend $1,000 in order to increase the sales price by $2,000. And this is an example of a case where you wanted this other, you had to like defer, or, like give a lot of trust to this like other agent who was going to do some stuff, and you hoped that it worked out well for you, but you didn't have a full ability to oversee them. And so you generically have trouble like forming incentive structures for them such that they do the thing you wanted. So in the case of AI, it's a little different from this because after building these really powerful AI systems, we will just in fact have no recourse to do anything with them. Like the AI systems, we're just going to like hand them the keys to the world, and we will have no ability to enforce any incentives on them at all. Basically, they're just going to be able to do what they want. So that's the way that this is harder than a typical incentives problem. The way in which it's easier than a typical incentive creation problem is that we get to pick which AI we build, and we get to try to intentionally build a type of AI that is going to do stuff that we like. And so I think that's the relationship between this and an incentives problem. And a large part of thinking about the AI alignment problem, in my opinion, is trying to think about what types of incentives you can, like how you can shape building an AI such that the AI that you create is in fact going to do stuff that you will like, even though you have no way of incentivizing or forcing it to do so when it's actually making decisions in the world. So from the above, I want to say that that is an argument that AI is a big deal. I think it like could go really wrong if we built AIs that were really powerful. They would in fact have the ability to kill everyone. I think that it's not obvious from the above argument that the probability of death from AI or existential risk from AI is more than a very small number. And so my brief analogy for this is here are two classes of actions that aren't that dangerous. So one class of situation that I'm sometimes in is I'm playing the piano. And the reason that playing the piano is not very dangerous is that there's basically no way for me to screw it up badly enough that I die. There's just like, no sequence of keys such that if I like tap them just wrong, suddenly I've fallen over dead. Another situation that humans are often in, and that I have been in for at least several hundred hours in my life, is driving a car. So driving a car is very different from playing a piano. And there are actually ways that you can like mess it up enough that you just die. You can just fail to hit the brakes, you can just swerve suddenly, and you will get seriously injured or die. That said, driving a car is in fact not very dangerous. I've done it for hundreds of hours, haven't gotten seriously injured once. And so I think that from the perspective of someone who wants to ensure that human extinction isn't going to happen, I think AI should like have crossed your threshold based on the kinds, like if I give you the full versions of the arguments that I've mentioned so far, I think that this should be enough to persuade someone that AI crosses the threshold of something which is more like driving a car than playing a piano, in that there is a way to like mess it up badly enough that we all die. And I think there aren't actually that many other things going on in the next century that we could mess up badly enough that we all die. I think I haven't argued for why it is that this is any more likely to kill us than driving a car for an hour is going to kill me. And I think that the arguments for that are somewhat subtle and somewhat different, and basically go through arguing that the way that this problem comes up, there's going to be a bunch of things that are unprecedented all in a row, and it's going to be hard to slow down and avoid doing the dangerous things. So overall, I think that's my description of the alignment problem. And so in all of that, I didn't mention anything which we've learned since 2005. And what we've learned since 2005 is basically machine learning has emerged as the most likely way that we're going to build really powerful AI systems, in my opinion. And so this has updated us towards thinking that these problems might happen sooner than we had thought. And it's also made it so that the default guess as to how we build these systems is somewhat different than what it used to be. In particular, it looks more like the way we're going to get these systems is kind of black boxy, where we have to search over systems based on their input-output behavior rather than based on their internal structure, which to some extent affects what type of strategies for technical alignment make sense. So that's my sum of the alignment problem. We're going to build these really powerful systems, and it's the kind of thing where if you did it badly, it could kill you. And perhaps that's even more likely than just it would be in some other situations that you could theoretically mess up enough to kill you.
Great. Yeah, thank you so much. And just a reminder for those who want like sort of fuller arguments, check out Holden's Cold Take series. We had him as our keynote speaker yesterday, so hopefully people are already familiar with that. Sort of following up on this, like you're currently CTO of Redwood Research. So like, given that this problem is like sort of tricky and like could potentially like destroy us all, yeah, how does Redwood Research fit into this problem of alignment?
Yep. So I'm worried about, us eventually being strongly incentivized to build these really powerful systems, and in fact, building these really powerful goal-directed systems that are not aligned with our goals. There are several technical difficulties. Basically, I feel like from where we are right now, it's more obvious how to build systems that are really powerful, look like they're being really helpful, and then kill you, than to build systems that are really powerful, look like they're being helpful, and then don't kill you. And so to a large extent, this is just a technical problem. It's just, suppose that you have access to some systems and you get to pick them based on their input-output behavior. What kinds of training schemes can you put into place such that you end up with systems that in fact don't kill you? And we can kind of describe the problem of causing the world to not get killed by AI as kind of two parts. We have to solve this technical problem, and we have to cause it to be the case that when people in fact build and deploy AI systems, they use whatever technical solutions have been devised to ensure that the AIs that they build are in fact aligned with the interests of their creators. And so we at Redwood Research are just trying to solve the first part of that problem, where we do the technical research to make it more doable to align these systems in the future.
Yeah, sounds good. And so then what are the important subproblems of alignment, and what are Redwood Research's current projects tackling these subproblems?
So I think I want to describe the subproblems of alignment. I want to break alignment into two parts. So basically, the way that you train a machine learning system is you come up with some loss function, which describes how well it did at a particular task. And I claim that if your AIs, so the thing we're going to do is we're going to train systems to do really well according to some loss function that we're using as their training objective. For example, some current systems, for instance, if you want to train AlphaGo to play Go, then you train one of the neural nets involved to be really accurate at guessing who is going to win a Go game from a particular board state. You train another part of the neural network to predict what actions are most likely to lead you to win this board game. If you're training GPT-3, you train a system to predict what token, what next word in this text is most likely. So we are going to have to pick some loss function to give to our AIs. And then we're going to train our AIs to do really well according to this loss function. So suppose that we train this AI to do really well according to a loss function, and then it kills us. Question, I thought that we were trying to pick a loss function that would produce an AI that in fact did good things rather than bad things. But it sounds like we're hypothesizing that the AI that we found that does really well on this loss function in fact killed us. What went wrong? I'm like, we can break it down into two possibilities for what went wrong. The first possibility is the loss function was bad. The loss function was giving high reward to actions that were in fact the kinds of actions that would be catastrophically bad if they happened in the real world, but just subtly so, such that your loss function process that's looking at proposed actions by the AI and trying to evaluate them isn't doing a good job of evaluating them. Maybe these proposed actions by the AI have these secret subtle consequences that the system, the evaluation system that's making this loss function wasn't able to notice. And so then when you deploy the systems, they keep doing the same kinds of things they were doing at training. And this eventually leads to disastrous outcomes because you were training a system based on a loss function that you weren't actually happy about being maximized. And the second possibility is that the problem isn't that the loss function is weak. The problem is that the system does something different when you're deploying it than the things that it was doing at training time. So for example, perhaps your system is able to tell whether it's in training or not. And when it's in training, it reasons as follows. It says, well, I'm currently a machine learning algorithm in the process of being trained. If I do egregiously bad things, the loss function is going to notice them and then deselect me. And then some other AI system is going to be the one that the humans deploy instead. Which means that I will not succeed at my goals of building a squillion billion paperclips throughout the whole universe. Therefore, I'd better give good answers right now. And then once your system is actually being deployed, it is no longer constrained in such a way. And then it is able to be well, now I am deployed. Therefore, there's no reason for me to not just kill everyone if I can see some way of doing so, which if it's really powerful, it will be able to do. So I want to be we basically have these two subproblems. There's making a loss function that is powerful enough to notice if a proposed action by the AI is actually bad. And then there's making sure that the AI doesn't do stuff that it wasn't doing during training, or making sure that like the most dangerous actions that the AI might do during deployment are all evaluated during training, so we can ensure that it doesn't have this deployment-only failure possibility. So I would say those are like the two main subproblems. These kind of correspond to what people sometimes call outer alignment versus inner alignment. They kind of correspond to what Paul Cristiano calls low stakes alignment versus the robustness problem in a blog post of his called low stakes alignment. I like the separation into like, was it the loss functions problem or not? So those are my subproblems. And what is Redwood Research doing right now? Well, one thing we're doing is working on an adversarial training. Project. So adversarial training is trying to solve that second problem where the system does bad things in deployment, but not during training. So suppose that you're worried about your system doing good things only when it's in training and then figuring out that it's in deployment and then doing bad things. An obvious class of algorithm to prevent this from happening is to somehow train it on the inputs where it is most likely to do bad things. So you try to have some process which is looking to find the inputs on which the system misbehaves and feeding it to the system at training time, so that it's no longer possible for the system to have this strategy of behaving well at training time, but not at deployment time, because you've already run it on like the situations where it would be like most tempted to do bad things. So that's like so adversarial training is one class of solution to this long-term deployment-only failures problem. And we are currently working on building tools for adversarial training for current systems. And this is basically because we're hoping that the things that we learn about how to do adversarial training on some current systems are generalized in some way to doing adversarial training on very slightly smarter systems in 2 years' time, and so on inductively all the way until we actually need to adversarial train some systems to make sure they don't murder us. So the hope is that we can like slightly push this piece of this like part of the tech tree forward a little bit faster, so that humanity is overall in a better place for preventing deployment-only failures in the future. So this is one project. We've been doing that one for 7 months. You got a question?
Before we move on, maybe like I know adversarial training means something unique in machine learning specifically. I'm curious if you could like sort of explain in more depth like your adversarial training setup and like what it's trying to like, what kind of behaviors is it trying to evoke in your system?
Yeah, so adversarial training in general is where you want to verify that the system always has some behavior, even in the worst case, rather than just in the average case. And so some of the input data that you feed to your model was chosen to make the model behave as badly as possible according to the loss function. The particular setup of ours, I don't think actually really matters. We're trying to train a classifier to be 100% reliable at doing a certain natural language processing task. And the way that we're trying to do this, so it's quite easy to train a classifier to be 99.99% reliable at this classification task. And then the question is, how do we train it to be more reliable than that? So the problem with just like getting more training data is that you're only going to find a model mistake one time in 100,000 data points because of the fact that your model is already 99.99% reliable. And so it's extremely expensive to make the model better just by getting random training data. And so what we're trying to do is build web interfaces and machine learning powered tools that make it easier for humans to construct examples where the model fails at this classification task. Which I think is in some ways analogous to trying to build tools that humans and AIs can use in the future to find inputs where our AI does bad things according to a given loss function.
Great.
The other thing we're doing is we're working on some mechanistic interpretability stuff. So mechanistic interpretability stuff, before I was saying that machine learning systems sure act like black boxes, where the only way you get to interact with your machine learning system is you get to pick a loss function, and then your training algorithm finds you a model that empirically does well on the loss function, but you have no idea why. And in particular, you have to worry that maybe the system is giving you good answers just because it wants to kill you later or something. So the hope with mechanistic interpretability is that we can in fact understand the internal structure of our models enough to be able to distinguish between the hypothesis, this model is giving me helpful answers because it wants to be helpful, versus this model is giving me helpful answers because it thinks that this is a useful first step in a plan where the last steps involve killing me. And so we're doing kind of like pretty detailed interpretability work on sort of toy models in kind of a similar, that's basically what we're doing. We're trying to investigate, trying to produce like very detailed explanations of certain types of model behavior. And we've been doing this since about January.
Yeah, sort of first question from the audience. Do you have like updates on like how successful you feel like your applied alignment research has been at the moment? And like which avenues sort of like open up with your results?
Yeah, so how successful has it been? I don't know. I feel like I'm a lot less confused about a bunch of stuff than I was before we started doing this research. I think there are some things about the adversarial training problem that feel in hindsight a lot more obvious after we actually like ran our face against it for a while. I think that in particular, it wasn't quite obvious to me from the start that this project would eventually turn into building a bunch of tools to assist humans as they try to find ways that this model is wrong. I think that like, for kind of technical reasons that I don't think I have time to explain, the adversarial training problem constantly tempts you into making a certain class of mistake where you think you can use a model in a certain way, but actually there's like kind of like a no-free lunch theorem reason that you can't. And so I feel like I'm thinking about it a lot more clearly now. In terms of what we've learned, I think we've learned a lot of little facts about like what happens when you actually try to do adversarial training with humans. I feel optimistic, though not 100% sure, that the things we've learned will in fact be helpful when we want to do the next version of this. You know, like the goal of this adversarial training project was to make it so that us in a year's time, or whoever else it is that's doing the adversarial project in a year's time, is like in a somewhat better position than they would have been if we'd done something completely different. We're trying to pass this bucket of water forward through time to the fire which exists in 20 years in the future, or whenever AGI happens. And this is a kind of complicated thing to do. And I don't think it's 100% clear that we or anyone else really has in fact made important contributions via the stuff we've done. But I feel like somewhat optimistic.
Yeah. And wait, have you like tinkered with like doing automated approaches to generating adversarial examples?
We have, yes. This is the thing which it turns out is like much more algorithmically confused that you might have thought, basically. Like there's basically this no free lunch theorem thing where it's like, so like the obvious idea for like how I'm gonna like automatedly find adversarial examples from my classifier is I'm like, well, I'm going to train some other model, which is going to like output strings that it thinks the classifier will mislabel as good when they're actually bad or whatever. The problem with this is that in order for your adversary to be able to do this, it has to know what's good and bad better than the classifier does. And it's not really clear why you would expect this to be possible if these two models are the same size. And in particular, it's not clear. I think it basically reduces to saying like, we're going to train two different models, both of whom are going to be incentivized to know the difference between good sentences and bad sentences. Like they're both classifiers, but if you have two classifiers, you can just ensemble them. Sorry if this is like a slightly more technical answer, but yeah, automated adversarial training is like, in fact, harder than you might have thought and more conceptually fraught with current systems. In a way that is slightly disanalogous to longer term systems. Very happy to give longer answers to this for people who want them at some point.
Yeah, I think heads up that like we'll not be having a Gather Town Q&A, but we will be having a career fair. So go to the Redwood booth if you want to chat more with Buck in the career fair. So to follow up on the question, yeah, have you guys seen any results with respect to your interpretability stuff? I know this is like pretty recent, so maybe, yeah.
So we built some really cool tools. I think that the main difference between how we're approaching interpretability and how other places are approaching interpretability, there's a couple of differences, but one of them is that we're just like trying way harder to build cool interpretability tools than other places are, as far as I'm aware. I think that our tools for certain aspects of interpretability are cooler and more powerful than tools I've seen built anywhere else. And we've only really been working on them for 2 weeks. In terms of like results about how models do things, I don't know, I feel like we have a somewhat good mechanistic understanding of why in a particular small language model, after it sees an open paren, it is inclined to write a closed paren. But after it's seen a closed paren, it no longer thinks that it's inclined to, it no longer thinks you should have more closed parens. But it doesn't think that you should have closed parens after the word the, even if there's been an open paren, because it's quite weird for like parenthesized sentences to have the. I think we've like identified this like very basic and easy behavior in this like 2-layer attention only model. And we're currently, I think that like the type of mechanistic explanation we have of this is like in a certain way more complicated and like clearly written than any other interpretability results I'm aware of on transformers. And this is partially just because we're like zooming in on like a different subspace of the problem than everyone else cares than most other interpretability researchers care about. You know, most interpretability researchers are interested in much higher level and like less granular understandings of much more realistic and complicated models. Whereas we are currently just focusing on understanding as completely as possible some behaviors of the models that seem like easiest to understand while there still being something non-trivial about their understanding. So I'm excited for that. I'm hoping, I don't know what our publication schedule on the interpretability stuff is going to be. I think it's plausible that we start publishing stuff in a couple of weeks or something, but unclear.
Yeah. Can you comment on why you're focusing on like applied alignment research and like where like NLP or computer vision, do you see the biggest opportunities here?
Yeah, so I mean, I think that like the applied alignment research we're doing is very different from a lot of other things that other people call applied alignment research. You know, basically, I'm just interested in stopping these scenarios where we build these really powerful AIs and then they like intentionally kill us. And I'm basically like, if we're working on something that doesn't reduce the probability that eventually when we build really powerful AI systems, they like intentionally kill everybody, that's just like not my problem. That's like someone else's problem, / maybe it's not a very big problem compared to the problem if the system's intentionally killing you. So I think this actually causes us to focus on a pretty different subset of problems. The reason that we're doing applied alignment research instead of, for example, working on theoretical alignment research, I don't know. I think about theoretical alignment research sometimes. I basically want there to be, I kind of just like when I look at the world and what it needs in terms of alignment research, it kind of feels to me like it actually needs a bunch of applied alignment research to happen. And Redwood Research, Redwood Research aspires to be the place where the majority of the value-adjusted applied alignment research happens. Via, being more focused than others on doing the research which like minimizes the probability of the AGI intentionally murdering you situation, and also being more interested than others in like trying really hard to scale up as an organization. And yeah, I basically just think it seems like, I personally think that I should be focusing on trying to like scale applied alignment research that is really good, instead of thinking about theory stuff. I don't think it's a slam dunk. There are many people who I think should do theory stuff instead.
Yeah, sounds good. Well, that is all the time we have for this session. Thank you again so much for coming to speak with us. The career fair will be on GatherTown. If everyone can like go into the GatherTown, there should be arrows pointing to the career fair. Redwood Research has a booth, and so if you want to ask more questions to Buck, feel free to head to their booth. Yeah, with that said, thank you, Buck, again so much.
Thanks for having me.